All right. So last time we had looked at the concepts of PyTorch. And as we had discussed that in the first half of the course, we have developed a very good understanding of how neural networks are put together. A simple type of neural networks are put together in layers. So for example, we'll put a column of neurons and we refer to this as a layer. And we can have as many layers as we feel like it. And we refer to these as linear layers if there's a single column of neurons, right? And the universal approximation theorem that we had talked about some time ago indicates that rather than having many, many layers of these neurons, if we pick two layers with a nonlinear activation function, then it can learn any complex decision boundary, or it can model any complex mathematical function. Okay, so two layers with a nonlinear activation function can learn or model any complex mathematical function. Doesn't matter how many curvatures are here, right? And doesn't matter whether it's in 1 dimension, 2 dimensions, 1,000 dimensions. That's what we need. We just need two layers, provided we use enough neurons in the hidden layer, right? Okay, so typically our general idea in building complex or deep neural networks is what we will do is we will use more than two layers, but the purpose of the initial layers will be what we refer to as feature learning. And once they have learned some features, right, then we will linearize them. Okay, so whatever our input data is, and doesn't matter if input data is in 1 dimension, 10 dimensions, 1,000 dimensions, right? We'll pass through some stages over here or some layers over here. And their goal will be to enhance those features that are important in recognition of the data, right? So once we have linearized it, whatever the network has learned, then we can put this two-layer, what we call it, a classifier, if our goal is to do the recognition. And then depending upon however many categories we wanted it to be categorized, we'll put that many outputs over here, right? So whether we are building a transformer-based architecture, whether we are building a convolutional neural network-based architecture, or these days we have what are called state space models are also getting attention. It doesn't matter what they are. All of these different type of architectures, we'll use them in the beginning to enhance or learn about the complex properties of the data, right? So that's what we call feature learning. And once the transformer or the CNN or the state space model has enhanced it, then, like I said, we'll transform it to, again, a simple linear layer, because if you take a look at two-layer neural network, it expects the input to be a column or a one-dimensional, sorry, n by 1, like a vector as the input. Okay. So anyway, from that point of view, as you can see, the concept is very simple. Okay. So now the next question is for this feature learning, which one is better? Is the convolutional neural network a better approach, transformer a better approach, state space model a better approach, or a simple linear, another linear layer or set of linear layers can also be used as feature learning mechanism. So which one is better, right? And of course, as you go along, you will recognize that depending upon the type of problem, one type of architecture may be more suitable for a type of problem, right? But equivalently, because see, all they're doing is enhancing some of the features, right? And this is doing the complex job of categorizing. If you had two categories, let's say X's and O's, the complex job of separating it into two or more categories is being done by the classifier. And the theory, mathematical theory, is well established that if we put enough neurons over here, it will be able to learn, provided we have enough data, right? Okay, so from overall concept point of view, as you guys have seen, in the beginning, whatever feature learning architecture we put in over here, whatever two-layer set of neurons that we put over here, or column of neurons that we put over here, two columns of neurons, okay, all of them will have some weight matrices. For example, we have talked about here, if you have, let's say, 100 neurons in the first layer and 50 neurons in the second layer, then the weight matrix will be 50 by 100 or 100 by 50. Both ways you can make it work, depending upon how you do the forward operation. So you can see there are weight matrices over here, and of course some biases. There are weight matrices over here in the feature learning process, as well as the biases over here. And some nonlinear activation functions could be over here. They could be over here. Okay. So in the beginning, all these weight matrices or the biases are initialized randomly, right? So for example, let's say we have a 50 class problem. Meaning we want it to be recognized into 50 different categories, right? So then how many outputs will you have over here? 50, right? Okay. So now let me ask you a question. And I may ask something similar on the final exam. Okay. You are given some data. Okay, it doesn't matter what type of data it is. You initialize your network. And of course, all the weights biases are initialized randomly. And you start passing the data through it, okay, through your network. What will be the accuracy of your network if you have not trained it? You are simply initialize it randomly and you observe, let's say you pass 100 data items and you observe what category is it recognizing. And because you already know the ground truth, you can compare the accuracy, okay? So what would be the answer? What's that? I want a number. What's that? No, there's one exact answer. Yeah. Let me give you a hint. Okay. What's that? No. Okay. Let me give you a hint. If you take a coin, right, and you toss it heads or tails, and you toss it 100 times, what would be the, how many times will it get heads? No.
Half.
You will do very poorly in gambling.
50%.
If you toss a coin, what's the probability of getting a head? 50%. So if you toss it 100 times, 50 times you'll get heads, 50 times you'll get tails. Okay. So let me ask you over here. You are random, everything is random. You're observing how many times it produces the correct output. Okay. Okay, it will be 2%. Okay. Because see, it is randomly picking, right? So for example, if you have a 10 class problem, okay, what's the accuracy as you start out? 10%. Okay. So the way, as you set up a network and if you're training it, how would you know, for example, you set up some network for a 10 class problem. Okay. How would you know it's learning or not as you go through different epochs? Okay. And the answer is if it is giving you 10%, 11%, 9%, depending upon the data. So what does that mean? It's hovering around 10%. It's totally random. It's not learning anything. Okay. So anyway, coming to our problem, like I was saying in the beginning, all the weights and biases are initialized randomly. So of course, for a 50 class problem, I will give you 2% accuracy. What would we like it to be? What's our goal here? To get it to be 20%? No, we want it to be 100%. Okay. So remember, this is how we set up our problems, right? We will define a loss. Loss, as you know, will have a single scalar as one output. So for 50 class problem, what would be the target? Meaning, what is the expected output? It will also be 50 numbers, right? Most of them will be zero, except for the category which we are trying for this network to learn and recognize correctly. Others will be zero. So we compare these 50 target values with the 50 actual values that our network is producing, right? And what kind of loss we will apply to it? For a 50 class problem, if you were setting up this network, what would be a good loss function? Cross entropy, right? So now you will go 50 over here, y of I, log of a of I, and minus, this is your loss function, okay? So once we have the loss function defined, right, as we discussed, what you will do is you'll feed in some training data, right? It will go through the network. It will produce some actual output. We can easily compute the loss. And then we can go back and now we can adjust the weights in the biases, right? And as we discussed compactly, how do we describe the learning process in the stochastic gradient descent algorithm? We will modify every parameter as theta. So theta represents weights and biases. Okay, and we will represent theta minus lambda as the learning rate, partial L over partial theta, right? If you have 1 million weights and biases over here, as you can see, this will be done 1 million times, right? But as we develop the theory in the deep learning class, we don't do it 1 million times because we represent all of our computations in terms of matrices. Okay, so if you had, let's say, 5 layers with 50 by 100, so you may be doing it 5, 6 times at the matrix level, okay? But anyway, we repeat this many, many times. We feed the training data. Stochastic means we don't feed it in the same order. Every epoch, we will mix the order so that it learns to generalize a little bit better so that on the unknown data, it can do a good job, right? So we've already developed all the math. How do we compute the loss? How do we compute these partial derivatives? Then we further, talked about if we are putting a lot of layers, a lot of data, a lot of high dimensions, then we can also use batch normalization. What does it do? How does it affect the gradients? How do we compute the deltas? In the very last layer, we also talked about we can convert it into a probability distribution by instead of using a normal, let's say sigmoid or some other nonlinear activation function, we can use softmax so that the sum of the outputs over here, if we add them up, so remember this symbol represents the sum. So if we added all the outputs, if softmax is being used in the last layer, what will this come out to be? 1, right? And that's why I say softmax converts it into the output into a probability distribution, right? So we also computed the derivative of the softmax and how it affects the delta calculations. Anyway, so we know the whole process exactly how we'll go inside and compute all the derivatives, train it. And you guys did it in assignment number 5. If I remember correctly, you did batch normalization, you did dropout. Then further, you also program the Adam optimizer so that individually, so let's say, suppose this is the loss function, and let's say this is W1, okay? Meaning if we vary W1, how is the loss? Remember, our goal is to make the loss become as low as possible, right? So if we are over here, for example, right, take a look over here, what will happen? The derivative of this, which is the slope, right? So, so this is partial L over partial W1. So how will we adjust W1? We will say W1 equal to whatever the current value of W1 is, which is over here. So this is the current value of W1, right? Whatever that is, 1.8 or whatever, doesn't matter. So the current value minus the slope, right? So first the learning rate, which is typically fixed something like 0.01 as an example, right? And then partial L over partial W1. So if the slope is high, right? If this derivative, so derivative is same as the slope. If the slope or the derivative is high, what will happen to the W1 value? Will it be adjusted with a higher value, or there will be very small change in W1? See, if this is high, right? You can see then we are subtracting a bigger number from here. But if the slope is very low, let's say the loss landscape happens to be something like this, and you are here. Now you can see slope is very close to 0, right? So you can see will change very, very slowly. Okay, so the problem that we run into in training of these large or deep networks is because this loss landscape, meaning how quickly is the derivative changing, every weight has a different loss landscape, okay? So if we try to, for example, let's say this was the scenario for W1. This was the scenario for W2, right? So what did we do to W1 over here? We changed it quite a bit rapidly, okay? So if we also change this, you know, this may end up somewhere over here. So so the purpose of the Adam optimizer was, okay, let's adjust at a high level each weight individually according to its slope, okay, or its derivative. Okay, so anyway, it had a little more theory in it that we went through. But anyway, so we know how batch normalization, how dropout, how Adam works, right? Okay, so as we discussed in the previous lecture, now that we have understood how the whole things are put together, what's the idea, now we want to be productive, right? So now we want to be experts. Our next goal is to be experts in PyTorch so that all these concepts can be put together and we can create huge networks and solve bigger problems in a short amount of time, right? So now let's come to PyTorch. So PyTorch is our most popular deep learning library as of now. Okay, and as I hinted to you in the previous lecture, prior to PyTorch, TensorFlow was popular. Still, some people use it, but 99% of the research that's being done these days, papers are published with reported results in PyTorch. So I will advise, even if you have worked with TensorFlow before, it's okay to know it, but really moving forward, I don't see any future for TensorFlow. Let's just focus on PyTorch. Tomorrow, if some other better library comes and the whole world starts to follow it, we'll also follow it, right? So my philosophy is don't go by what you like, go by what the rest of the world is doing in the technology field, okay? So as of now, like I said, PyTorch is the gold standard. So the good thing about PyTorch is it's very easy. It behaves very similar like a normal programming language. The only difference is that in a normal programming language, let's say you are programming in C or C++ or Java, right? You declare variables and then you write expressions, right? So typically, most of the time in normal programming, either we operate on individual variables or we operate on arrays of data. And maximum we go is two-dimensional arrays, right? Uh, PyTorch has a concept of high-dimensional arrays. So we'll be dealing with tensors. Okay, so tensors are multi-dimensional arrays. Okay, so for example, okay, let's say you have some images are given to you, right? And images are, let's say, 500 by 300 pixels, okay? Further, let's pretend each image is a color image, right? So then in PyTorch, we refer to this as a channel, okay? So then further, we will have for our color image, typically there's a red, green, blue. So further, we will get 3 into 500 by 300. So 500 rows, 300 columns, and every pixel is a combination of red, green, and blue. So however, in PyTorch, we'll describe it by three-dimensional data or three-dimensional tensor, right? Now, as we discussed, if we set up a network, right? Okay, whatever data we are feeding during the training process, we will not feed one at a time. We'll feed a batch of data. Okay, so if our batch size is, let's say, 16, right? Then as you can see, and each image is 3 by 500 by 300. So you can see now we are feeding in 16 by 3 by 500 by 300. Okay, so this will be our size of the tensor. So you can see it's a four-dimensional tensor as it's flowing through the network, right? So in PyTorch, we have a concept called shape, and we also have a concept called size. They're both pretty equivalent. Okay, so the shape is, again, basically means the size in each dimension. Okay, so for example, shape of 0 in this example will be 16. So this is called dimension 0. This is called dimension 1. and so on, right? What will be shape of -1? Okay, -1 basically means last in Python, right? So shape of -1 or shape of 3 in this example is the same. Okay, both of them will be what in this example? 300. Okay, so often, like I said, in PyTorch, the variables become multidimensional. We refer to them as tensors. And then further, you have to manipulate some of the dimensions, and that's what a lot of our programming will be. Otherwise, it's very similar to a normal programming language, right? Okay, so now from PyTorch point of view, how our setup will look like. Okay, any given problem that we are going to model or program, right? First thing you will do is you will define your data. Okay, so you will have some training data. Okay, so this training data, for example, let's pick a simple example. It could be set of images. Okay, which means somebody has given to us like folder or folders. And, sometimes if it's a multi-class problem, so you will have a parent folder, then each class will have its own files over here for images as an example. And then here's the class 1 and so on. So if it's a multi-class problem, whatever your training data is, it will be given to us in some kind of a foldered structure, right? So from setup point of view, what we will do is PyTorch requires two things for you to create. One is called the data set, and one is called the data loader. Okay, so the job of the data set is to store all data. Okay, as you can guess, for example, let's pick the same example. We have these 500 by 300 images, and let's pretend they belong to 50 different classes. Okay, so what you will do is you will now start to read the data from all these folders, and you will start to store them in some tensors. Okay. Let's pretend our training data in our example is, let's say, 100,000 images. Okay, which means because we have 50 categories, let's pretend this is a balanced data set. So that means each category has how many images? 2,000, right? 2,000 times 50 will be 100,000. Okay. So each category, so anyway, so as you can see, if we were to store all data, right, as one tensor, so what will it be? It will be 50,000, sorry, 100,000. Okay, then each is 3 by 500 by 300. So you can see in our data set, one possibility would be create a tensor of this size, start reading each image and start storing it in our big tensor, right? So shape 0 is basically the image number. Shape 1 over here is the channel. Shape 2 is rows. Shape 3 is columns, right? So that is the idea behind the data set, store all data, right? Then what is the job of the data loader? Job of the data loader is to obtain a batch of data from the data set. Okay, so now so which means one of the key specifications in the data loader will be batch size. So you will indicate what is the batch size, whether batch size is 16 or 32 or 64, you will decide. And so data loader will keep going to the data set and will keep saying, give me, let's pick an example. Let's say batch size is 16, give me 16 images, right? So the question is, should those, if I put all these 100,000 images, so let's say these are 100,000 images, okay? Here's one image, two image, right? And the 100,000th image. So the question is, if this is how the data set is storing, will the data loader give us first 16, then next 16, then next 16, right? And the answer is during training. Remember, during training, what do we want? We want all the data in complete sequential order, or we want it randomly chosen. So during training, because our algorithm is stochastic, won't we need to convert the data set to a tensor data set? Yeah, I'm giving a high-level idea first, then we'll come to the real details, okay? So anyway, during training, we want the data to be stochastic, meaning every time we ask, it should be a different set of random 16 images, okay? So typically, as you will see in PyTorch, at a very high level, you will create the data set, okay, which means store all data. In this example that I'm trying to, so that we can easily understand it, we are storing all the images, right? Then we will create 3 data loaders. Okay, why 3? Okay, typically one will be train data loader. Second will be validation loader. Third will be test loader. Okay, so we divide the data typically in 3 parts, train, validation, and test. Okay, so for example, let's go back. We are given 100,000 total images. We may decide to have 80,000 be used for training, 10,000 for validation, and 10,000 for testing, as an example, okay? You can change these numbers. You could have 70,000 here, 10,000 for validation, 20,000 for testing, but I'm just giving you a rough idea. We'll break this data in 3 parts. So going back to our data set over here, where we had 100,000 total, right? What we will do is this first 80,000 we will use for training, then 10,000, then 10,000 for testing and validation, right? Okay. So as we create the data loader, okay, at this time we decide on randomization and batch size. So 2 things we will decide. Whatever data we are getting, should it be randomized, or should it be in sequential order? And also how much data the data loader will obtain. Okay. So like I said, for training purposes, what is the requirement? Should we do the randomization? Yes. You have to randomize the data, otherwise your model will train, but it will not do a good job on the test data or the validation data, right? So randomization, definitely yes. Okay. For the validation and testing, do we need the randomization? No, because that's the unknown data. It doesn't matter because we're not using that to train the system. We are using both of these to test the system. So randomization, no. Okay. Batch size over here. So what will be the batch size for training purposes? Okay, that depends on the data set. For images, uh, typically for images, we use slightly large batch size. For example, 3264 is a popular choice, okay? For natural language processing, the batch sizes are typically less. For NLP, the batch sizes are like 8, 16 maximum. Okay. Um, the keep in mind, how is the batch size going to affect the performance of our model? Okay. Remember what is batch doing? If one is saying change the as we compute the derivative is in this direction. Second is saying here. Third is saying here, right? So as we do the average gradient, it will tell us, okay, average gradient is over here, so that even if one of these is not agreeing or noisy data, we will proceed properly in the direction where we should be going, which minimizes the loss for most of the time, right? Also keep in mind, as we create deeper and deeper networks. Okay, so going back over here, let me go right. As we are doing the feature learning, one of the things we also do over here is batch normalization so that we get stability in training. And batch normalization, what does that mean? Uh, Normalization generally means subtract the mean and divide by what? And divide by standard deviation, right? Okay, so if the batch size is small, will the mean be more stable or it will keep varying from batch to batch? Okay, see if you have a lot of data, right? To give you an example, suppose we have 100 students in our class, okay? I divide these 100 students into a group of five, and take the mean of the five, then mean of the next five, then mean of the next five. Will these means be similar to each other or they'll vary a lot? They'll vary a lot, as opposed to I divide a group, put it into groups of 20 and then take the mean, right? So you can see larger batch size stabilizes the means and the standard deviation. But the only thing is we will have to run it for a lot of epochs so that it gives us as good of accuracy because we're modifying the gradients. So to give you an example, if you have, let's say, we picked 80,000, right? Of our example trained data set. If I say, oh, let's use a batch size of 1,000, okay, then if I divide 80,000 by 1,000, what will I get? 80, right? That means how many times I am updating the gradients, the weights and the bias? I'm only updating it 80 times, right? On the other hand, if I say, no, instead of 1,000, let me use a batch of 100. How many times I'm updating this? 800 times. So potentially it will train faster with a smaller batch size. The only thing is it may be slightly unstable, meaning sometimes you will see the loss goes up. So how could you tell as you are whether your batch size? So there's two things as you are training a network. Let me give you a guideline. Okay, one key issue is the batch size. And another key issue is the learning rate. Okay, so if every epoch you print the loss, okay, if the loss is gradually going down, as you see, these are the, let's say, epochs. Okay, in the beginning, right, in the very beginning, of course, the loss will be very high, and then the loss will continue to decrease, right? Okay, so if the behavior is like this, that means you have a decent batch size, decent learning rate, okay? But if your training loss goes like this, okay, every epoch it goes down, goes up, goes down, goes up. Okay, that means either your learning rate is too high or batch size is high or small. Small. Because remember all in the batch normalization, it's subtracting the mean, and so the data is widely varying, so it's unable to proceed in a good learning direction. So anyway, as a guideline, like I said, for images, if you have a new type of data, you will start out maybe a batch size of 32, I would recommend. Okay. And learning rate, these days we have pre-programmed optimizers. So for example, Atom Optimizer is a popular choice because individually it can adjust the learning rate for each of the individual parameters. And the default learning rate for Atom Optimizer is 0.001 or 1 e⁻³ right? Okay, so you can leave it at default, but I'll give you an example. One of the research I'm doing right now is working on a new transformer architecture. Okay, and as I am experimenting with it, okay, I find out because it's different from a normal transformer architecture, then if I use even 1 e⁻⁴, it does not learn. Okay, and again, how do I know it's not learning effectively? How do I know? The loss goes up, goes down, goes up, goes down, goes up. After a lot of training, it does get better. Okay, so even 10 times less as the default Atom for this type of architecture is not working. So the best learning rate that I start out with is 5 e⁻⁵. Okay. And then after a little bit, after 100 epochs or so, I reduce it to 2 e⁻⁵, then 1 e⁻⁵. Below 1. So if the learning rate is too small, then again, because remember, we are using this learning rate to adjust the parameter. If this is too small, it's not going to move at all, right? So anyway, coming back to our learning, so let's summarize it. So you will create the data set. Data set will store all the data. Okay. You will create 3 data loaders. Every data loader will decide on whether you will use the randomization and what batch size you will need. Okay. For the trained data loader, the randomization has to be selected. If you forgot to do that, it will not be effective it will not do a good job on the test data and the validation data. So randomization has to be done, right? Batch size, as we discussed, typically 32. It could be 64, it could be 16. Sometimes I have seen as high as 512 batch size. Okay. For the validation loader, randomization, no. And test loader, no, because there you can just go and sequence, test it on this, and you can have as high of a batch size. Okay, for example, you can have a batch size. Let me ask you this. Can I have a batch size of 10,000? In our example, remember we said validation is 10,000, test is 10,000. Can I have a batch size of 10,000 for my test loader? Okay, and the answer is you can, provide it fits into the GPU's memory. Okay, because remember, what does that mean? That means, see, typically this, as you create the data set and you store all data, this will be typically stored in CPU's memory, not GPU's memory. Only when we are training, we will use the GPU, which means the train loader, as it goes and brings, a batch of data, this will be converted to GPU's memory. Okay, so now imagine you are asking it from the GPU 10,000 times 3 times 500 times 300. Okay, and multiply that if you have a 8 byte. So anyway, if you find out how many bytes this is, it may be that your GPU cannot handle all of this. So then you will cut it down to 100 or 10 or whatever. The smaller the batch size, the better it will, from a memory point of view, it will be able to handle. The only thing is now because you have to test on the entire 10,000 data, so you will have to loop through it if the batch size is 100. As an example, to go through 10,000 images, you'll have to loop through 100 times, right? Okay, so anyway, train loader, validation loader, test loader. So our typical setup, like I said, so coming back to our setup, okay, you will create the data set. Once again, store all images. And this will be in the CPU's memory. Okay, then you will create data loaders. Okay, here, two things you have to select: randomization and batch size. And you will create train, test, and validation data loaders. Okay, then third thing you will need to do is define the deep network. Okay, fourth thing you will do is define the optimizer. Okay, and okay, define train, test, validation loops. Okay, so this is the typical architecture of when we create a deep network. Okay, so I'll give you a high-level example of real code. Then I will come to your assignment 6, 7, and 8 and show you how you will do all of these things. Okay, so let me go pick one example. Actually, this is not a good example. Let me pick some other example. Open. Okay, so here's a simple example of a PyTorch data set. Okay. Um, so if you take a look over here, uh, so you'll see in the project, there are a few files. Okay. One is called utils.py, one is called mydataset.py, one is called network.py. Uh, so typically what I do is everybody has their own style. Okay. So the train test validation loops, I tend to write it in the main file. Okay. The data set where we store all images, I'll create a separate class for it. Like in the example I was just showing you, I called it my data set. Of course, you'll pick a meaningful name for it. Okay. Uh, and the data loaders which associate with the data set, usually what I do is I create a file called utils.py. And inside it, I put a simple function which will create the data loaders and return the train test validation data loaders. Okay. Um, the deep network, whatever we are defining, this will again go in a separate file. For example, you can call network.py. Okay, optimizer and the training loops, these go together, and I put them in the main file. Okay, so again, if you want to organize it slightly differently, I leave it up to you, but that's my, my style, and a lot of the code you'll see on the internet also follows something similar. Okay. So let me just clarify that at a high level through an example, right? So you will create a new project. You'll, of course, set the Python environment. Okay. Now, because we'll be using PyTorch, right? So the assumption is, let me go back over here. Let's go to our deep learning website. Okay, so if you go to handouts, okay, hopefully you guys have already gone through its software installation instructions, Visual Studio, PyTorch, right? Where we talked about how you will set up the PyTorch environment. And hopefully you guys have a GPU on your system. That will really help the rest of the course. If you don't have a GPU, I highly recommend go to the one of our AI labs and program rest of the assignments. Uh, if you try to run it on your laptop, even if you have a GPU, don't run it more than 5 minutes, because then it generates a lot of heat, and laptops are not designed to handle the GPU type of computing. Okay, so anyway. Once you have set up so again, this part, if you haven't done it yet, make sure you do it properly by going to the handouts and following the software installation instructions, especially the PyTorch part, right? Okay, so now once you have installed PyTorch, it will give you some libraries that we need for creating deep networks, but not all libraries, right? So some of my handouts are old. I should upgrade them, but So let's say, let me give you a hint over here. Okay, so let's say you created a PyTorch environment. And suppose, because once you create an environment, it asks you for a name. Okay, let's say you named it PyTorch 2x. Okay, because they keep coming up with version 2.5, 3.5, right? So I just call it 2x. Okay, so suppose that this is the environment you already have created. You've installed PyTorch in it, right? And now you need a library called pandas. Okay, because by default, it will not give you all the libraries. So how do we add this library to it? Because if you try to run import pandas as PD and it gives you an error, cannot find pandas or whatever, right? So the best way to do that is on your computer, go to the command prompt. Okay, you may have to run the command prompt as an administrator. If it doesn't allow you, first try it without the administrator. Okay, in our AI labs, you don't have the administrative rights, so it won't let you run as an administrator. But if you just launch the command prompt, it will work, right? So first thing you will do is you will say activate your environment. So activate PyTorch 2x. So you will see right in the beginning over here, I am inside the PyTorch 2x environment, right? Now, if I install any library, if I say pip install and name of the library, pandas, it will install it in that library. Okay. You can also install these through Visual Studio, but I used to do that. So that's why some of the handouts, even if they are showing you screenshots, I'm installing a library through Visual Studio. Don't do it directly through the command prompt. That works better. Okay. Okay, so going back to the example I was trying to show you is, okay, let's take a look at how the data set looks like, right? Okay, so you will see in this example, there is self.x, there's self.y. Okay, so in this example, the x will contain all the training data and y will contain all the targets. Okay, and depending upon the size of the problem, right? This will be, for example, different for each type of data, whether it's images or not. In this case, I was just creating, this is a standard Python data set, which is two-dimensional data, like red, blue type of dots. And I wanted 200 items in this data, right? Okay, so the data set class that you will create, the base has to be torch.utils.dataset. Okay, and then you will store all the training and the targets in some variables over here, right? As you create, because the base class is dataset, there will always be one special function you will need to write called the length, which will give you how many times you have to loop through possibly, or how much data there is. Okay. Then one function has to be get item. Okay, where whoever is invoking this my data set will give us one index. For example, if they say, give me data at position 5, okay, then it will go and pick the 5th data item in this tensor and corresponding 5th target over here, right? Okay, so anyway, so this is what it is returning the data at that particular spot. Okay. Uh, so that was the just a high level idea of the data set. Let's take a look at, so going back to this example, like the high level idea. So once you have created the data set and you have all the data stored in it, like X and Y, right? Okay. Now we need to create the data loaders, right? And like I said, most of the time what I will do is I will go create a file called utils.py, write a simple function over here, something called get loaders, and return, create the 3 data loaders, train, test, validation, and return it. So in this example, I may not be creating all 3. Let me go to utils.py. Okay, so in this example, I just was created, I didn't divide it into 3 data loaders. So this simple function get data loader, and you can see the batch size is 4, right? So torch.utils.data loader, we are creating one object from the PyTorch library, associating it with the data set, and shuffle equal to true. Can you guess what will this do? It will randomize the data, okay? And it will return the data loader, okay? So anyway, and I have some other support functions to be able to visualize the data. Third thing, what do we need to do over here is define the deep network, okay? So whether you are creating a linear network or convolutional network, so in this example, I have this my network class over here. Okay, so the network that we are creating, right, has to have a base class torch.nn.module. Okay, this is how PyTorch works. In the def init, you can add some parameters over here. Okay, but basic idea is you will define what building blocks you need, okay? For example, in this case, I need a linear column of neurons. If you take a look at FC1, right? The linear is declared with what's the size of the input and what is the size of the output. And of course, that defines how many neurons are there, right? So let's say somebody triggers it with hidden size of 50. So you can see the FC1 will have 2 inputs, but 50 neurons, right? FC2 will have, if hidden size is 50, let's say output size is 2, so then it will be 50 times 2. Then we need a ReLU activation function, softmax active. So these are just the building blocks we need in our network. The forward function now decides how the network is put together. So for example, if we go to, let me put this side by side. Okay, so in this example, as you can see, let me just move it more here. Okay, so so you can see the X data will come in over here. So just for, so we're seeing how the network is put together, and that is decided by the forward function. This function always is called forward, okay? So if you see X equal to self.fc1 of X, so that means this will pass through FC1, and we are still calling it X. Okay, we could have called it X1 or something, but anyway. Then what happens after we pass it through, we apply an activation function. And what is act? ReLU. So over here, you will see the activation function. Let me just put over here. It will apply ReLU to it, right? Then what is it doing? Let's go to the inside over here, self.fc2 of X. So now this is passing through FC2, right? And then further, it's being given to the softmax. So this is our softmax and return X. So this is our output. So this is how the forward function is put together, right? Goes through one linear layer. Let's say the hidden size is 50. You'll see there are 50 neurons over here, right? Then hidden size times output. So this is 2 neurons over here. In the softmax. And so this is how it's put together. ReLU over here. So just 2-layer network, right? So this is the job of our network class. Once again, base has to be torch.nn.module. And now let's go to how the whole thing is put together. Okay, so going back over here. Okay, so now we have to tie it to an optimizer, train, test, validation loops. In this example, I don't have test and validation loops. I'll show you another example soon, but we just have our train loop. So let's see how that is done. So the main is this classification nn.py is the main. Okay. And I also forgot, we also set up the loss function over here, right? So loss function is mean squared error over here. We could have set it up as cross entropy also, like you see in the comment. We call the get data loader to obtain the data loader. We define the loss function. We define the, for example, optimizer. This could be Atom as well. So there are many options or simple SGD over here. We create an object of the network class, right? And then we will go into this training loop over here. Okay, one of the confusing things, a lot of people, if you take a look over here, we created the network over here, right? So can you guess what is this doing? Net.train. Okay. So in my opinion, they picked a terrible name for this function. Okay. People in the beginning get confused. Oh, this is training the network. Okay. No, it is not training the network. All it does, it sets the network in the training mode so that it can start to compute the gradients and you can adjust the gradients. So this only, so let me give you a big, it might take you some time to absorb and you'll keep forgetting it. So anytime you create any model, right, or net or whatever, and you say model.train, and you have two options, model.eval, okay? So this basically sets the network in training mode. Okay, means gradients can be computed. So it allows the gradients to be computed. Okay, eval sets the model in evaluation mode. So here, no calculation of gradient calculation or update of gradients allowed. So when we are testing our model, we will set it in the evaluation mode. When we are training our model, we will set it in the train mode, okay? But simply calling train does not mean it's going to train, okay? So coming back over here, you'll see, so our typical code goes like this. We will define how many epochs to train, right? Then if you see in enumerate data loader, okay, so to explain this part, right? Let's pick an example. Okay, there was a question. How to reset the model? Okay, I'll come to that in a second. Okay, so let's first try to understand the enumerate data loader. Okay, so to give you an example, let's say we have batch size is, let's say 800. Oh, sorry, let me pick 100. Batch size is 100, and our trained data is, let's say, 80,000. Okay. So what does that mean? So if I draw the picture, right? Let's say, so we have total of 80,000 training data, right? During training, are we going to go in sequence? No, we are randomly going to pick, right? So the question is, how do we randomly pick? Pick one over here, pick one over here, pick, right? How are we going to pick these 100 items randomly? And the answer is, rather than picking those randomly, we'll still pick them in sequence, but before selecting the 100, we will shuffle this data. You know, like a deck of cards, you shuffle, then you go pick the first 10, then the next 10, right? So that's the idea. So first shuffle the data so that it will mix everything up. Then you can go, you still have 80,000 over here, but these are shuffled now. Now, if you pick 100, 100, right? So in the first epoch, you will see the 100 you're getting is totally mixed up. And before you start the second epoch, what should we do? Shuffle it again. Okay. So if we shuffle it again differently, you know, it's like you're playing card game. Every time you start again, you shuffle again, right? So the 100 you pick, will it be the same as these 100 if this was shuffled before doing this? So it will be different, right? So that is the idea. So my question is, the definition of the epoch is that we want to go through entire training data one time. Okay, so this is the definition of the epoch. So my question is, in our example, if we have 80,000 training data, 100 batch size, how many times we should go through it for one epoch? Each time, remember, we ask it, it will give us 100, then next 100, right? So as you can see, we'll go 80 times, correct? Going back over here to this code, enumerate data loader. Okay, and again, let's pretend we have 80,000 training data. Remember the way it works is, let me draw one more picture. Okay, so let me draw one picture. So we have data set. We have data loader. Remember, whenever we create a data loader, we tell it which data set it should use and whether it should use the randomization, whether it should use what batch size it should use. Those are the two things we do when we create a data loader, okay? And this has now, let's pretend 80,000 data in our example, right? So remember, as we go and we create this data loader object, so we create data loader. Okay, so now it has tied it to a data set at that time, because over here we will indicate data set, whatever the name of the data set is, we will indicate shuffle equal to true. We will also indicate batch size over here as we are creating the data loader, right? Okay, so in our training loop, okay, we want to every epoch, we want to go through this 80 times, right? So this is where, if you go take a look over here, enumerate data loader, automatically will, in this example, it will take us through 80 times. Okay, so this loop will go through 80 times. Each time it will tell us batch IDX, which will be a number. For example, 0, first time it will be 0, then 1, then 2, then it will go up to 79, right? And each time, what will it obtain? 1x and 1y. Sorry, not 1x, as many x's and y's as the batch size. Okay. And once we obtain this, then if you take a look over here, what is this going to do? This is going to convert it to device. What exactly is device? Typically, what we do is in the very beginning, we will say torch.device CUDA. If CUDA is available, CUDA is our NVIDIA GPU, LCPU, so that we can run this code either on GPU or CPU. So anytime we want to convert a given tensor and put it on the GPU, we have to do is say to CUDA or to device. Device already has been set to hopefully CUDA if you have a GPU. Okay, so anyway, so this is basically converting the X and Y that we obtained from the data loader to the GPU, right? As I mentioned, data set is typically stored on the CPU. We don't put it on the GPU because it may be too huge to fit into the GPU's memory, okay? Okay, so how do we reset the model? Optimizer.zeroGrad. Once we create the optimizer, so take a look over here. This is how optimizer was created. Torch.optim. This could be Atom or SGD. Okay, when we create the optimizer, we tie it to a particular model, a particular network. So in our case, what is net? That's the two-layer network I just showed you, right? So whatever are the weights and biases over here, the optimizer knows which model it has to adjust. Okay, we specify the learning rate, and if there's a SGD has another parameter called momentum, we can also set that up, right? Okay, so anyway, optimizer.zeroGrad will go to the network it is associated with and zero out all the weights and biases. Okay. Sorry, I shouldn't say it will zero out all the gradients, not the weights and biases. The weights and biases are initialized randomly. The gradients will be zeroed out. Okay. Outputs equal to net of x. Okay. So in PyTorch, like I was saying, once you create the network, okay, you write a very special function called forward. Okay, so anytime you create an object of the network and pass it a data, it will implicitly call forward. We rarely call forward function explicitly. So in the main training loop, you will see, okay, when we say net of x, this net is our network that we had defined earlier and created earlier. And this will end up calling the forward function, right? Okay, of course, it will produce the outputs. Okay, as it produces the outputs, we'll now trigger our loss function, give it the outputs that the network produced and the target. Where did we obtain the target? From the data loader. See, anytime we go through the data loader, batch IDX XY. So X is the input and Y is the corresponding expected output or the target. So loss function will use both. In this case, what loss function did we create? Mean squared error. So we'll do the mean square error. And once we say loss dot backward, so in PyTorch, automatically will do the derivative. So here's the beauty of PyTorch. We don't have to calculate any of those partial derivatives. So in case some of you did not feel comfortable with math, don't worry from now on. At least on this part, there won't be any math. All the derivatives, all the deltas will be automatically computed by PyTorch, okay? And optimizer.step, now it will do theta equal to theta minus lambda partial L over partial theta. So it will, this one line step will update all the weights and biases in our network, right? And then we just keep repeating, keep training. Okay, there was a question over here. Will CUDA work with Apple Silicon chips? I think, to my knowledge, even the Apple is using NVIDIA GPUs. CUDA is NVIDIA. So if your computer, doesn't matter what brand it is, so CUDA is NVIDIA. So as long as you have an NVIDIA chip for the GPU, then CUDA will work. And when you install PyTorch, you are given an option whether you are, see, okay, the CPU may be an ARM, but I'm pretty certain some of the Apple laptops do have NVIDIA. You guys have NVIDIA in your laptops or no? Oh, those are not Apple? I thought for some reason you did. Okay.
They ship neural chip, right? Some kind of neural. Yeah.
Okay. We can easily find out. So like I was saying, when you go through the setup, what you will do is you'll Google PyTorch. Okay, once you go to the PyTorch setup, okay, see over here, it tells you you have a Mac option over here. And okay, for Mac option, there's no CUDA. CUDA is not available for Mac OS. So, but anyway, if you have Linux or Windows, then you have CUDA 12.4 is the latest as of now. And this is the, so all these instructions are given in your setup. Okay, so if, what I will recommend is, yeah, without CUDA will be, yeah. See, for computer science or AI, I know some people love Macs, but you run into more headaches then it's worth it, in my opinion. So anyway, that's your choice. Okay, so coming back to our overview first. Okay, so hopefully that gives you an overall idea of how we will set up this entire thing, right? So let me give you a few minutes break. And after the break, I'll go over some of the assignments that you will be doing this week. So this week, I'll give you 2 or 3 assignments so that you guys can be productive. Okay, let's take a short break. Hey, so to summarize, as we discussed before the break, our total architecture is, once again, you will create a data set. You will store all data. Okay, so typically you will have X and Y tensors over here. Y is the expected output, X is the data, right? There will be a very special function over here called getItem, which will return 1X and 1Y. Okay, and of course there was the length so that we can enumerate over the data set and go through all the data, right? So with this data set, now you will associate one or more data loaders, and you will decide on the randomization and the batch size, right? So then you will create your network. However many layers, whether it's a CNN or a transformer or whatever, doesn't matter. It will produce some actual outputs. The target you will get from your data loader, which as it's obtaining a batch of data, it's feeding. So this batch of data is being fed to the network, right? Then as you guys saw in your main, you will also specify the loss, which loss function you're going to use. There are pre-built loss functions in PyTorch. So some pre-built loss functions, and we can create our own loss functions as well. Okay, so we can, as you will see as we go along, we can create our own loss functions as well. Okay, so once we compute the loss, right, or whether we are using pre-built or create our own, then as you guys saw, you will do loss.backward, and this will compute the gradients, provided the model is in the train mode. So make sure the model is in the train mode. So if you already have set up model.train before you started your loop, right? So loss.backward will compute the gradients, and loss.step will update weights and biases, as you guys saw. Sorry, not lost. Optimizer, my mistake. Optimizer.step. See if I quickly take you. Okay, loss.backward will compute the gradients, and optimizer.step will do the update of the weights and biases, right? So this will update weights and biases, optimizer.step. Okay, so how do we organize this? Like I was telling you, I put this in a separate file. I put this in a separate file. I typically put it in a utils file along with some other functions, and the whole training loop and setup of the loss and the optimizer goes in the main function. Okay. So anyway, once you've seen a few examples, you'll get used to it. The good news is overall architecture is pretty easy to follow. And of course, depending on the type of the problem, it will keep changing. Okay. One of the things that changes is, for example, as we are creating the network, right? Sometimes the network will take one input, like one tensor. Sometimes it may take two or three. So as you set up the data loader, you will, the type of data you're returning will vary. So let me show you an example. So in one of your assignments, you will be, I think it's assignment number 8. So I will assign it so that, because time is short, so that now you have enough overall background that you can start to do all these assignments. So in assignment number 8, as an example, I'll show you one of the things that you will do is you will create what are called Siamese networks. And let me give you a brief idea of it, why they are important. So there's a field of AI. It's called contrastive learning. Okay. Just like the name indicates, contrast means we're comparing two things, right? And seeing how they differ from each other. So basically, in plain English, basically means compare two things and learn the differences between them. Okay, so for some type of learning problems, the contrastive learning works better than the normal learning that we have discussed, where, for example, the loss function, let's say for multi-class classification, what did we discuss? What is the best loss function? Cross entropy, right? So let me give you an example and show you why cross entropy does not always work well, okay? And the example is face recognition. Okay, so how many people are in the world? I forgot, like 6 billion or whatever, right? So let's pretend it's 6 billion. And if we wanted to do face recognition so that we give a picture of a person and immediately recognizes who this person is in the world, what class problem is it? How many? 6 billion class problem, right? So as you can see, it's even if we somehow got it to work, it won't be very accurate because there's so many subtle differences. For example, you may know somebody who's a twin and they are identical, and only their parents can recognize who's who. So for face recognition, like I said, cross entropy does not work well. Okay, so there are three pioneers in the world of AI. One is, Hinton, who got the Nobel Prize, and one is Yann LeCun. So Yann LeCun and his students came up with this idea of contrastive learning. And so they defined another loss function. And this loss function, again, at a high level, the idea is, if, let's say, you're taking a look at, easy way to understand is you're taking a look at two pictures. Okay. Okay, so let's say, this is the famous soccer player Ronaldo. Okay, so this is picture 1 of Ronaldo. This is picture 2 of Ronaldo, taken, some other time, slightly different pose. Okay, but it's the same person, right? If it is the same person, from loss point of view, we should see that the loss should be less as we compare these two, right? But if it is one of these is Ronaldo and the other is, let's say, Messi, they are totally different people. So then it should produce a bigger difference between the two, right? So their idea was that for these type of problems, if we do contrastive learning as opposed to a cross entropy or mean squared error type of learning, we'll be able to do a better face recognition. So pretty much all face recognition systems, if you go to the airport or driver's license or whatever, if they're using face recognition, it's based on this contrastive loss, okay? So what is this contrastive loss? In assignment number 8 as an example. So this is the equation for the contrastive loss as was created by LeCun and his students, right? So what is y over here? Remember, in our terminology, what does y indicate? Target, right? And dw is the distance, okay? So let me give you a tiny bit of information. So if I have, let's say, one vector, let's say v1. Remember, vector is just a column of numbers, right? For example, this is a 3 by 1 vector, 1, 2, 3. Suppose I gave you one more vector v2, minus 1, 2, 4. Okay, this is also 3 by 1 vector. So in the three-dimensional space, both of these are simply points in a 3D space. Okay, and of course, there's a concept of a distance. In the mathematical terminology, we often call it, if it's a straight line distance, we call it Euclidean distance. Another name for this mathematical, in the mathematical terminology, is L2 norm. Okay, often we represent it as, for example, D1 minus V1 minus V2. Like these two bars often are indicated to mean distance or Euclidean distance or L2 norm. They mean the same thing. How do we calculate it? Okay, this is a number, okay? Like a distance is a number. Okay, for a 3 by 1 vector, all you have to do is subtract the corresponding and square it. So 1 minus minus 1 square plus 2 minus 2 square plus 3 minus 4 square root. So this will be my L2 norm for the V1, V2. Okay. So what will this come out to be? 1 minus 1 square. This will also be plus 1, 0, 0, 3 minus. So it will come out to be 1 as an example. This was too easy of an example. Okay. But anyway, so the point is you just subtract the corresponding and square it and take the square root, and that's the distance, right? You already know in your high school math where you only dealt with XY coordinate, if X is 3, Y is 5, 4, 7, 2 points, right? And the distance is 3 minus 4 square plus 5 minus 7 square root is the distance. So in high dimensional spaces, like I said, again, corresponding values, square and square root, add and square root, right? Okay, so coming back to our contrastive loss. So dw is the distance, just like I showed you between two vectors, okay? So when we set up a Siamese network, what we do is we create two networks which are identical. Like I said in this picture, same parameters, same structure. If it's a set of linear layers or CNN layers, doesn't matter, both are identical. We'll feed one input over here and another input over here. For example, this could be picture of Ronaldo, and this could be a different picture of Ronaldo, okay? as we go through over here, through these networks, remember at the very end, what do we do before we pass it to the classifier? Let me take you to the beginning of today's lecture. Okay. So as I mentioned, what is our typical setup? Our typical setup is we pass the input. Okay, then it will do some feature learning, and then what will it do? Okay, we'll linearize it. Okay, so suppose we linearize it to 100 by 1 vector, right? So you can see before we go to the classifier, there's always a linear layer. When we were discussing CNNs, let me refresh your memory. So let's go to CNN architectures. So if you recall, in one of our previous lectures, we went over the architecture of CNN, right? Am I right? Did I go over it or not yet? Not yet? Oh, I haven't covered the CNNs yet? Okay. All right, then I'll go over it maybe in the next lecture. Okay. So in a CNN, what we do is we feed in an image as an example, right? It will go through what we call convolutions. I thought I already had covered it, but maybe I forgot. Okay. Anyway, somewhere over here, you'll see we are producing 4x4 as one of the outputs, another 4x4. So it's two-dimensional. So then what we will do is 4x4, if you take a look at a 4x4 set of numbers, it is total 16 numbers. So if I go to the first row, put the first 4 numbers, then second row, put the next 4 numbers. So I linearize them, meaning put all the 16 numbers in one column, even though it's two-dimensional over here, right? So for each one of these, if I put over here, in this example, there were 6 of these, okay? So 16 times 6 will make it 96 total numbers. And if I'm putting 50 neurons over here, this weight matrix will become 50 by 96, right? But if I just focus on this part, because this part is the classifier, right? Then how many numbers do I have? 96 in this example. So you can think of it as coming back to our assignment number 8. Okay, we pass it through some CNN network, one image, and this is the linear part, the 96 by 1 vector I was showing you, right? Whether it's 96 by 1 or 100 by 1, we can, set up the sizes accordingly. But you'll see there's one vector over here, one vector over here. So 2 vectors are being produced over by the 2 networks. So you can think of this as one vector over here and one vector being produced over here. Okay, so what is DW then? DW is the distance between these. So once again, if you have picture of Ronaldo, let's call it R1. Picture of one more, let's call it R2, right? So we pass it through the same network. Okay, we get one vector, we get a second vector. Now we compute the distance between the 2 vectors, okay? So then that is called DW in our loss function. So let's go to the loss function. Okay, so this is our loss function over here. Okay, so DW is the distance, okay? So the question is, what is Y? Okay, if the picture is for the same person, okay? So let me go over here. Okay, let me just go a little bit higher. Okay, so our loss function is half dw square and 1 minus y plus, so let me go to the equation. 1 minus y half dw square plus y. So plus y max of m dw. Let me just double check. Max of 0 m minus dw. Max of zero m minus dw, and y is further being multiplied by half and then square. So there's a half over here and square over here, right? So this is the loss function, which we refer to as a contrastive loss. Okay, so let's try to understand it. So what was the dw? dw was the distance between two pictures of Ronaldo, right? So y, remember, is in our terminology is the target. So the way we set up is if it is the same person, meaning or the data belongs to the same class, then the expected y is 0. Okay. If it is the different person, then expected y is 1. So this is how we'll set it up. Okay. So now let's try to understand it. Okay. If we give picture of Ronaldo, right? Two pictures of Ronaldo. Okay. Then my question is, what will be y then? It will be 0, right? So what's 1 minus 0? 1. Okay. So half dw square. So do we try to increase the loss or reduce the loss? See, our goal is always when we are making the network learn to reduce the loss, right? So since we are always trying to reduce the loss, my question is, what should it do to dw, which is the distance between the two embeddings of the two pictures of Ronaldo? Should this distance become larger or should it become smaller? Smaller, right? If the two pictures that we are feeding to the two parts of our network are for the same person, then what did y will be? 0. So then second term, we don't have to worry, okay? So all we do is, so in other words, going back to our learning, right? If we are during training feeding two pictures of Ronaldo, the loss that we calculate will be based on the distance between these two vectors. If the distance is high, what will we do? We'll go adjust the weights, right? It's the same network. So we will adjust the weights for one of the network because like I said, it's the same weight, same biases. Okay. So that now if we feed the same two pictures of Ronaldo, the loss will be a little bit less. So that is the idea over here. Now to understand the second part of the equation, what if one picture is for Ronaldo and the other picture is for Messi? Okay, so one is Ronaldo, the other is Messi, right? So now my question is, because this is during training, so then what will be our target then? Target will be 1 because we already know that we are feeding them two different pictures, right? So if target is 1, what happens to the first part of this loss? 0. So we don't have to worry about this part. Now focus on the second part. Y now is 1, right? For the time being, let's pretend. Okay, so let me rewrite this so a little bit clearly. It is y half max of m minus dw squared. Okay, m is fixed. So this is sort of like the upper limit. Okay, e.g., for example, let's make it 3. Okay, suppose we feed in, once again, our example is Ronaldo and Messi, right? Okay, y is 1, so we don't have to worry about this part. Okay, so from a loss point of view, the question, we are always trying to minimize the loss, right? So when will the loss become smaller? Let's say dw is at some point we feed into dw is 1. Let's pretend. If dw is 1, m was fixed 3. So what is 3 minus 1? Sorry, I missed the 0. It's max of 0 and m minus dw. Okay, so 3 minus 1 is 2. What is max of 0 and 2? 2, right? So you can see in this example, 2 square is 4. 4 divided by 2 is 2. Loss will come out to be 2. Okay, if the dw is 1. Okay, so my question is, should dw increase or decrease in this equation to reduce the loss? Because our goal is to reduce loss. So to reduce loss, should dw increase or decrease? Okay, see, you can right away see if it was 1, what if it becomes, this is 3, right? What if I increase it to 2? So what will happen? 3 minus 2 is 1. Max of 0, 1 is 1. 1 square is 1. So you can see loss becomes 0.5. So dw has to increase for the loss to become. So in plain English, now hopefully this will make sense. It's really very commonsensical. If the pictures belong to the same person, then should the distance between these two vectors increase or decrease for the same person? We want these vectors to be closer to each other, okay? If these pictures that we are feeding in belong to two different people, then what should this behave as? It should try to increase, right? So in the high dimensional space, let's visualize it. Okay, suppose this is a picture of Ronaldo. Okay, we feed in R1 to our network. And we are looking at this, we refer to this as latent representation. Like I said, as we pass through the CNN, right, eventually we'll flatten it. This will be simply a vector. Whatever that vector is, in the technical terminology, we call latent. Latent means hidden, because of our final decision, remember there's a classifier at the afterwards. So we're looking at the latent representation of Ronaldo. And let's pretend in the high dimensional space, if this is 100 in the 100 dimensional space, like I said, every vector is a point. Okay. So let's pretend this is the representation of Ronaldo. Okay. Now what we do is we feed in to the same network one more picture of Ronaldo. So this is also Ronaldo. If this network has learned fairly well, my question is the R2's latent representation, will it be close to this point or will it be farther away from this point? Close. So R2 will be somewhere over here. So let's say we had 50 pictures of Ronaldo. What will they do? They will form a cluster over here if we take a look at the latent representation. Okay, what about Messi? Messi might be over here, right? If we feed in more pictures of Messi after the network is fully trained, then and if it was trained to minimize the contrastive loss, what will happen? All the Messi pictures will form a cluster, right? Okay, so face recognition, like I said, really, because it's separating out. Uh, uh, Remember in one of the assignments, we had those red and blue dots, right? And if one red was very close to blue, you saw that it was not able to learn unless we overfit the model. So intuitively, what is contrastive loss doing to the network from learning point of view? It is creating a representation of each input data such that in the high dimensional space, they separate out from each other if they belong to the different category, or they come together if they belong to the same category, right? So if you run into a problem, which is a multi-class problem, okay, where the data is very difficult to distinguish from one class to another, right? And you try cross entropy and you see, oh, it didn't work as well. All you're getting is 60% accuracy, which is not that high. So what would be your alternative possibility? Contrastive loss. Okay. So now let's take a look at, let's go back over here, because our goal is if we can understand, right? Setting up the network is easy. As I showed you, pick up few building blocks, write the forward function and go through it, right? Coming up with really neat specialized loss functions to help in a particular situation is, one of the research challenges. So anyway, so coming back over here, now let's take a look at from training point of view. Okay, from training point of view, like from learning of setting up of data sets and data loaders point of view. So let me ask you this. If your goal was to create a contrastive loss network, like I said, creating network is easy. My question is, as we create the data set, as we create a data loader to tie it to the data loader gets tied to the data set, right? Because its job is to feed data to our network under training. So my question is, in normal training, let's say you were doing MNIST digit recognition. Okay, we only feed in 1x, right? And so the data loader through the get item, what does it return? It returns typically X and Y. X is your set of images in the batch and Y is the corresponding label or corresponding target, right? That's what it normally does. If we are setting up now a Siamese network, okay, how many images does it need? Does it operate on one image or more than one image? It operates on two images because it has to know, are the two same or are they different? So you can see what will the data loader do? It will return 2 images, and how many labels? And 1 label. Because remember, as we discussed, the label will be 1 or 0. If it is 1, what does that mean? No, 1 means different, 0 means same. Right? Okay, so let's see if I can show you how the data loader and data set were created. So in the assignment number 8, as you program it, right? We are not doing it for images. We are doing it for MNIST digits, which is easy to set up, right? So let's see. Take a look over here. So as you can see, our X and Y. Okay, if you take a look over here, X and Y have our all training data. X is the set of images, Y is the set of labels. So that's the easy part, right? Okay, let's take a look at the get item. If you take a look at get item, okay, so you'll see somewhere over here, let's focus on this part. What are we returning from the get item? We are returning 2 images, right? And we are also, are they different or are they the same? Okay. Then you can go further through this code to see how we are determining whether they are different or the same. But today the goal is to get a high level idea. So you can see our get item has to return how many images? 2, if we want to use it to train a contrastive learning, right? Now the get loaders is easy. All it has to do is tie it to the data set. Depending on the batch size, it will obtain this many pairs of data. Some will be same, some will be different, right? Okay, so in assignment number 8, as you go further, okay, let me talk about this a little bit later, but first let me show you one more thing. So Siamese network, where we have 2 identical networks and they learn to produce the latent representation such that it's close distance-wise in the vector space for similar classes and different, I mean, the distance is larger if the input pair belong to different classes, works well for difficult decision boundary type of problems. So Jan LeCun and his team also came up with another better network, okay, which they call a triplet network, okay. So the triplet network, if you take a look over here, how many inputs is it taking? 3, okay. So to give you an example, what's the idea over here? Idea is like this. Okay, X, for example, easy way to understand will be, okay, this easy way to understand this would be, pretend this is picture of Ronaldo, okay? So we're giving it 3 pictures, right? So what would X plus be? This is another picture of Ronaldo. So plus means it belongs to the same category. Okay. Okay, what about X minus? So this would be Messi. Yes. So that belongs to a different category. Okay. So as you can see, as we go along, right, there are 3 networks now. They are identical weights and biases. Each one of them will produce a latent as a vector, as you guys have already seen. All networks produce a latent, okay? So forget the loss function. Intuitively, what should be the distance between these two? What should it try to do between x and x plus? Should it try to increase the distance in the latent representation or reduce it? Reduce it, okay? So this one you'll see will try to, sorry, my writing on this one is not as clear. Reduce is what I'm trying to write. And here it will try to increase it. So simultaneously now it's, previously it was just taking a look at two at a time. And so why the three might be better, let me just show you. So in case of a Siamese network, right, if you are feeding two, okay, and it will, for corresponding, so it will try to, like I said, sorry, I should put it like this, okay. Okay, so we give it same, it try to reduce it. Then we give it different, it tries to increase it. It's like, it's sort of like the net behavior would be from a loss point of view, it may create fluctuations because one is trying to move it the other way, even though it's still learning properly. What I mean is, if we give it simultaneously, hey, look at now both scenarios and pick a representation that simultaneously satisfies both conditions, similar condition as well as a different condition. So that is the motivation behind what we call this triplet loss. Okay. So as you go through the assignment, okay, so let me go back. Okay, so from a data loader point of view, my question to you is, now what will be feeding it? How many items will the data loader be returning? What's that? Why 5? Because isn't it always guaranteed the right one will be same class and the left one will be different class? So all we need is 3. We don't even need the label. You guys agree or not? All right. So anyway, let's take a look at the overall loss function. See, do you guys see if it makes sense? Okay. So the center image over here is called the anchor. So if you see xi of A, that's the center. Okay, xip, can you guess is which one? The positive, the right one. Okay. And what about the xin? That's the negative one. So you can see this is our total loss, right? So what is this term over here? It's the distance between similar or opposite type of images. Similar. So the distance, should we try to reduce it or increase it? Reduce, right? Like I said, in the math terminology, if I say V1 minus V2, so that basically means the distance. Okay. So as you can see, if we make this smaller, the loss will go less, right? What about this one? Okay. See, there's a minus term over here. Okay. So that means take a look over here. So in other words, let me see if I can explain it to you. Okay, suppose the loss produced is 5 as compared to -5. Which one is smaller? The negative, right? So in the optimization world, if your goal is to maximize or minimize, we can always change the problem from minimization to maximization or maximization to minimization by simply multiplying it by -1. Okay, so had I put a plus sign over here, that would mean we also need to reduce this. But we don't want to reduce this. We want to increase this. So this negative sign will automatically take care of this. This alpha is, again, a constant so that, you know, we have a finite loss and it's not 0. So anyway, so loss function makes sense. Let's take a quick look at the Okay, so we can create our own loss, like I was saying. If we create our own loss function, like I said, there are some loss functions pre-built into PyTorch, like mean squared error, cross entropy. As you can see over here, to create our own loss function, the rule is the base has to be nn.module. Then we simply write a forward function and define the two equations that I showed you, where we do the square of the two terms. This is how we can create our custom loss function in PyTorch. Okay. Let me quickly show you the data loader and the data set. Triplet data set. Okay, so here, as you can see, I'm returning a list of 3 images. Sorry, let's go to get items, get item. Okay, so if you take a look over here, the get item, right? Does it need to return the labels? As we discussed, there's no need to return the target or the label. So at the very end of the get item, what's being returned? 3 images. Okay. So that is the, okay, so 2 more minutes, let me stop. So this week, what I'll do is I'll give you 2 assignments. Actually, 1 assignment, because I have not covered the CNNs with you. So assignment 6 is very easy. It's okay. So it goes over some of the basic concepts of PyTorch. I've tried to explain, you know, and like I said in the picture, if I say you need to install something, do it the way I showed you in the beginning of the lecture. Okay. So you will be creating simple examples with respect to classification, with respect to regression. So, so we have a category called classification that you already know. We have one more category called regression. So regression is where the network is learning to produce a continuous output. Okay, for example, you know, there's a field of AI, time series prediction. Your teaching assistant for the course, Musle over here, is expert in the time series domain, and his PhD is all tied to how do we, for example, it could be the stock market or the weather. You're given some history, right? And your job is to predict what will the stock price be next 2 weeks, or what will the weather be next 2 weeks, right? So you can see it's not, it's outputting a certain number. For example, if it's the temperature, it could be 71.2, then next number could be 65.3, next number could be 75.4, right? So when we make the network learn to output these continuous numbers, that is called a regression problem, okay? So in assignment number 6, for example, one of the things we'll teach our network is to learn to generate sine wave. Okay, and we'll see how it will produce the output, right? So one of the things as you program it through PyTorch is what activation function should we use? Because in the beginning of the lecture, I said for our network to learn any kind of complex function, the activation function has to be nonlinear, right? So we have 3 choices so far. What are our choices? Sigmoid, ReLU, and tan hyperbolic. So my question is, if we are creating a network to learn sine wave, okay, how does sine vary from? What is sine of 0? 0. What's sine of 90? Right? And so as you know, the sine wave varies from 1 to -1. So my question is, what will happen if you put a sigmoid as the activation function on the output? What does sigmoid vary from? 0 to 1. So if you train it, what will it behave like? Let me show it to you quickly. Okay, so the blue is the training and red is the predicted. So do you see for the positive side, it's able to learn. Why is it not able to learn the negative side? Because sigmoid doesn't go negative, okay? So you also have to think about, as you are doing a regression problem, what activation function should we use? Now, let me ask you this. Will ReLU work? ReLU will also, for negative, it will not work, right? So let me see if I have a picture of ReLU. Do you see like somewhere over here, there's like a complete straight line, because ReLU has this non-linearity. Oops. So ReLU function is, like this, and then like this, right? So because of this sudden change, it produces very sharp boundaries, okay? So this is the behavior for ReLU. So if you wanted to make it learn sine wave regression, what would be the best activation function? Tan hyperbolic, right? So tan hyperbolic, you'll see, oops, will look something like this, right? So go through assignment 6. It's pretty easy. Simple PyTorch concept. Same, we talked about data loaders, data sets. And next week, I'll talk about CNNs. And once you are good at CNNs, then you will do the Siamese and the triplets and so on. Okay. All right, I'll stop here for today.